everybody. So this is part 2 in a 3-part series talking about die casting design. And today we're going to talk about die casting defects. So where do they come from? And more specifically, how do we avoid them? Before I do that, again, let me just introduce kind of the format here, and most specifically the area where you can input questions and things like that. You can minimize this area by clicking on the orange button. That'll close the panel, and then if you click on it again, then it will open it back up again. And as we did last week, if you have questions, you can enter them real time. There's an area down there at the bottom where it says enter a question for staff. You just type in there and then push send, and then it comes to us. And as in last week, we will address all the questions at the end of the session. And again, you can input questions at the end of the session also. Again, this presentation is brought to you by the diecaster shown here. Apparently, you guys will all get a copy of this webinar. And so these are the guys that are bringing it to you, which is Daco, who's a zinc diecaster, Chicago white metal, aluminum, magnesium, and zinc. Technical die casting, aluminum and zinc, Lakeside Casting Solutions in zinc, and Solomex in aluminum, magnesium, and zinc. And as we talked last week, these are the guys you should be talking to, or any die caster is who you should be talking to, whether it's a local guy, your current supplier, or these guys here. They want to talk to you, and we'll talk about this again today in terms of talking to the die caster as soon as possible in the design process. And here's the reason why. We talked about this again last week, Mr. Chowdhury, and to quote him again, he's saying that most companies spend only 5% of their budget on design, but design typically accounts for 70% of the cost of the product, partly because 80% of the quality problems are unwittingly designed into the product itself. And so basically what we're saying is that decisions made by designers such as yourself, they will provide 80% of the problem, at least according to Mr. Chowdhury. So obviously, to design for die casting or any process, you really need to understand how the process works. We discussed this in detail last week, and now that we know how the process works, we need to develop a better idea of the characteristics of the process and how do these characteristics affect the quality of our die castings. So we started to develop a basic idea of this in the last webinar. So the question we're going to address today is where do defects in the die casting process come from? We obviously need to understand this so we can avoid design characteristics that will tend to produce defective castings. And today we'll mostly focus on porosity. Why do we focus on porosity? Well, a little pie chart on the right-hand side kind of shows why. This was a survey that was done by NADCA a number of years ago, and they went to end users such as yourself and said, what's the biggest problem that people have with die castings? Well, the biggest cut of the pie, porosity. 35% of the respondents said porosity, and then another 32% said other defects. Now, many of these other defects, as we'll see later on today and in the next webinar, many of these other defects come from or originate from areas such as porosity, and that's why we focus so much. So 32%, 35% gives you 67%, so basically 2/3 of the respondents are talking about porosity or porosity-related defects. So obviously we need to understand the mechanism for the formation of porosity in die castings. Both as designers we need to understand it, as well as die casters, and the idea is so we can minimize or control the amount of porosity we get in our die castings. And today obviously the focus is on the design side of things. So it's worth reminding everyone who's listening online that porosity is not necessarily a defect in the die casting process. It's going to be there in our castings no matter what. So it's worth saying that again. So porosity is going to be present at some level in our castings. So if we call all porosity a defect, that implies that any die casting with porosity in it is defective, and obviously that's not the case. Porosity is only a defect when it exceeds some kind of porosity specification in a casting, or maybe a portion of a die casting of specific interest to the end user. So this is really, really important to understand. Historically, people have often said that porosity is a defect. This implies that we just flipped the wrong switch on the machine, we made a bad casting, and that all our castings are going to contain some level of porosity. However, both the designer and the die caster need to ensure that the casting doesn't contain too much porosity. We need to make sure that the porosity level doesn't exceed the quality specifications for the casting. So today we're going to talk about 4 different things. We're going to talk about the sources of casting defects. We're going to talk about process control of defects, i.e. what the die caster can do to eliminate or minimize defects. And then we're going to talk about the design control of defects, what you guys as designers can do to eliminate or minimize defects in the casting. And then we'll talk for a few minutes about actually measuring defects within die castings. And so, as we talked about earlier, obviously the emphasis today is going to be on porosity. So let's talk about the cause of defects, and basically, therefore, we're talking about the cause or origins of porosity. So basically, there are 2 sources of porosity in die castings. There's solidification shrinkage. This is the volumetric contraction that die castings go through when they go from the liquid phase to the solid phase, and I should have said all castings. As we go from liquid to solid, there's a volumetric contraction. And unfortunately, as you solidify a casting, you solidify the surface of the casting first, so that rigidly sets the dimensions of the outside. And so we don't just get a shrinkage in each dimension. What happens is generally we get porosity, or pores, shrinkage porosity it's called, in the center of our castings. The other source is gas, and as we will talk about in a minute, there's various sources of gas porosity in all sorts of castings, and certainly in die castings too. Now, there's 2 types of pores that you can get. On the left-hand side, we're showing a pore. These are the black things here with the smooth surface, and generally those pores are formed at high fractions when there's lots of liquid around, and then we get the jagged pores shown on the right-hand side, and generally these are formed at lower liquid fractions. And so many other types of defects in die casting can also be related to these types of porosity formation. So for example, if we get leakers or hot tears or surface sink, these are often related to shrinkage porosity. If we get non-fills or laps, these are often related to the filling of the casting, and the problem can be related to gas entrapment. So many, as we talked about earlier, many of the different types of defects in die castings can be related to porosity. So if we look at the 2 photographs here, the smooth pore shown on the left-hand side, often this is thought of as a gas pore, while on the right-hand side, jagged pores are often thought of as shrinkage porosity. This is not quite accurate, so let's briefly describe how these pores form. So gas entrapment tends to form early in the solidification process, whether it's from air entrapment or some other gas. Generally, it's forming as the liquid metal is filling the cavity, so there's lots of liquid around, and this allows the gas pore to spheridize, and so we tend to get a smooth round pore. So this is just like bubbles in water, in soda, in beer. If you look at them in detail, they tend to be spherical in nature. There's lots of liquid around. The liquid doesn't affect the shape of the pore, and so it wants to minimize its surface energy, and therefore it forms in a spherical shape. Shrinkage, on the other hand, tends to occur right at the end of the solidification process. Basically, there's not enough liquid around, and so there's lots of solid around, and so the pore has to conform to the shape of the surrounding solid. So this is a bit like a gas bubble formed at the bottom of a fish tank. You've got a lot of rocks in the fish tank, and if you look at those bubbles that are forming, they basically conform to the shape of the surrounding rocks. And so that's basically how a shrinkage forms. So it's also important to understand that for most aluminum alloys, the volumetric contraction as we go from liquid to solid as we solidify the alloy, this is around 6% or so. So we should expect to get 6% shrinkage porosity. But when we look at die castings, it's rare to see a die casting with more than 3% porosity, and certainly generally less than 1% is more typical. So what this tells us is that we should expect to get 6% porosity just from shrinkage, but we're getting less than 3%, maybe less than 1%. So we're actually doing quite a good job of controlling the shrinkage. So let's examine this in a little bit more detail. Let's look at different alloy compositions. So if we look down here on the left-hand side, this is for different materials, and we can look at the solidification shrinkage. What is the volumetric shrinkage? And so pure aluminum, for example, we just talked about 6. It's actually around 6.5 or so. But if we add silicon to the alloy, and 12% silicon is eutectic, and most die castings, most aluminum die castings are aluminum silicon alloys. So if we look at 12% silicon, you can see now the volumetric shrinkage is reduced to only about 3.5%. So we can dramatically reduce the amount of shrinkage occur in the alloy, and as we'll talk about shortly, we can also dramatically change how the alloy solidifies. However, so that suggests we should just go with the 12% silicon, but as we'll see in a minute, maybe that's not ideal either. Let's talk for a minute about zinc alloys. Most of the common zinc alloys, the Zamac alloys, are about zinc 4.5% aluminum or so, and you can see, so the volumetric shrinkage is quite low for that, about 3% or so. Let's go back and talk a little bit about aluminum silicon alloys. So this again is volumetric shrinkage. This is aluminum with different silicon concentrations. And as I said, most die casting alloys contain somewhere between about 7% silicon and 12% silicon. So 8% silicon, that's a common alloy. And you can see that we've already reduced the volumetric shrinkage down to about 5.5%, and at 12% silicon, as we talked about before, it's already reduced to 4% or so. So let's talk a little bit about freezing range and different alloys, and we'll talk about how the alloy composition affects the way the alloy freezes, and also in terms of, therefore, how the shrinkage porosity is formed. So the first thing to talk about is that a pure metal will solidify at a discrete temperature. For aluminum, that's 660 degrees centigrade, 1220 degrees Fahrenheit. So that's the same as water, right? We think of water as freezing at 0 degrees centigrade and 32 degrees Fahrenheit. So pure metals are the same. They melt and solidify at a discrete temperature. Alloys, however, don't do that. And of course, most of the die castings that we produce are alloys, except for the aluminum motor rotors. Most of the alloys are most of the die castings are alloys, and they will solidify over a range in temperature. And so what that means is it will start, as we cool, it will start to solidify at a higher temperature and end solidification at a lower temperature. And how wide that range of temperature is depends on a number of things, but it certainly depends upon the alloy composition. And for aluminum die casting alloys, for example, it depends on how much silicon is present in the aluminum die casting alloy. So if I've got a lot of silicon in the alloy, the aluminum 12% silicon that I just talked about, that's considered a short freezing range alloy. And what that means is that the alloy freezes over a very narrow temperature range. And if I want to get technical metallurgically for a second or so, what I'm talking about is the difference between the liquidus temperature and the solidus temperature for this alloy is very, very small. So for aluminum 12% silicon, all the metal solidifies at roughly the same temperature. And when this happens, that gives us a very narrow mushy zone. And so that's what the figure on the top left here is kind of demonstrating. If we look at the diagram, basically we got a partially solidified casting that we're gating from the bottom up. Here's the gate. And we got solid. The dark gray material is solid at the surface. We got the white material that's liquid in the center, and the area in between is partially liquid, partially solid, and we call that the mushy zone. And the mushy zone is kind of similar to slush on a road in the winter. Slush is basically partially solid snow, partially liquid water, and so the mushy zone in the casting is kind of similar. It's partially solid material and partially liquid. And so the width of this mushy zone as the casting is solidifying is going to depend upon the freezing range of the alloy. And so a short freezing range alloy such as aluminum 12% silicon will tend to have a very narrow or thin mushy zone. Again, so if we look at the right-hand side, which is kind of a blow-up of that solid-liquid interface, you can see the black is the solid, the white is the liquid, and then the area in between is the mushy zone. And it's kind of partially solid, black, partially liquid, white. And actually what we're doing is we're looking at the structure of the dendrites, and then the shrinkage porosity is going to basically form in this mushy zone. So when we get a narrow mushy zone, it's very easy for the liquid to get to the pore and what we call the feed the shrinkage. And so when this happens, we get very little porosity forming as the casting solidifies. As we look at this diagram at the top right here, so we've got a pore that forms here. Well, there's liquid right next to it, so it's going to flood in and just feed that pore and get rid of that pore. And then if we solidify a bit further, we form another pore. Again, there's a ton of liquid around, and therefore it's going to feed it, come in, feed that pore, and get rid of it. So what this means is that as we are solidifying, whenever a pore forms, it's immediately fed by the liquid. And so therefore all the shrinkage, all the porosity in this type of alloy is going to form at the last part to solidify. Because we're going to, as we solidify, we'll feed it. As we solidify a bit more, we feed it. As we solidify a bit more, we feed it. And then at the end, well, there's no more liquid to feed it because we've run out of liquid, and therefore we get these big, large macro pores towards the center of the cavity. So with a short freezing range alloy, we tend to get one or only a few large shrinkage pores at the last part of the casting to solidify. So as we reduce the silicon concentration, so as we change the alloy and maybe we go to 8 or 9% silicon, we're going to increase the freezing range of the alloy. And so these are called wide freezing range or long freezing range alloys. And again, metallurgically, what it means is the distance between the liquidus temperature and the solidus temperature is increasing. And so we have a long freezing range alloy. And so if we look at the same kind of schematic on the top left, we've got the solid at the surface. But because of the wide freezing range, most of the alloy is mushy. We get very, very liquid, very, very little liquid remaining at the center of the casting. So again, if we blow up that area, we can see we get this solid plus liquid mushy zone. And in this case, when a shrinkage pore forms, then there's basically no liquid to feed it. So in this case, as we're solidifying, the pore forms, there's no way to feed it, and it will just stay there. And so with this type of alloy, with these long freezing range alloys, the pore will tend to remain wherever it forms, and therefore we get a distributed porosity of very small pores all over the casting. And these finer pores are often much more difficult to detect, much more difficult to find compared to the large macro porosity we were talking about for a narrow freezing range alloy. So what have we learned? We've learned that shrinkage can account for all the porosity we see in traditional die castings. So therefore, clearly we need to consider shrinkage when we're looking at designing a die casting. And if we want to minimize shrinkage porosity, we need to feed more liquid into the casting to provide more liquid to feed the shrinkage porosity. And the way we do that with die casting is after the cavity is filled, the plunger applies very high pressure to the biscuit, generally greater than 5,000 psi, maybe as high as 10 or 15,000 psi. Because what we want to do is push more liquid through the gate to supply more liquid to compensate for this volumetric contraction that's going on as the casting is solidifying, and we call this feeding the solidification shrinkage. So how do we reduce shrinkage porosity in die castings? Well, one thing is a bigger gate. The gate is how we feed the liquid into the casting. It's also how we feed the shrinkage. So a bigger gate will take longer to solidify than a narrow gate, and then we can push for a longer time and push more liquid into the die. Higher pressure applied by the plunger. Again, that's going to push more liquid into the die. We can change the alloy. As we've shown, by changing the alloy, we can dramatically change how the alloy solidifies and how the porosity forms, both in terms of its shape and its distribution. Now, one thing we haven't talked about yet, we've just talked about shrinkage so far, but gas entrapment is also going to form porosity in die castings. And actually, it often will interact with the shrinkage porosity that's been formed. Okay, so let's talk a little bit more then about gas entrapment and its effect on porosity. And as we can see here, there's really three major causes of gas entrapment. There's hydrogen. Hydrogen is the only gas that actually dissolves in liquid aluminum, and then it will precipitate out upon solidification. And if you look at the lower left picture, that's kind of very characteristic of hydrogen when you get small spherical pinhole porosity all over the casting. Then entrained air. Air is obviously pre-existing in the die cavity before we inject in the liquid aluminum or the liquid zinc or whatever we're casting. And if we don't get the air out, then it's going to become trapped in the casting as porosity. Then the third source is evaporation of any liquid that's existing in the cavity, such as a lubricant or water. Obviously, as we talked about before each cycle, we spray an organic lubricant on the die faces. We also put lubricant in the shot sleeve. And as we inject the hot liquid metal into the cavity, this can cause vaporization of the lubricants and produces gas that become trapped in the casting and producing porosity. And it's in die castings, one of the issues we have, it's often quite difficult to separate gas porosity from shrinkage porosity because gas often fills the shrinkage pores. But it's obviously really, really critical, as we'll see, because the way we address it, both from a design point of view as well from a process point of view, is very, very different. And if we're not clear what the cause is, then we're going to address it incorrectly. So let's talk about each one of these three types of gas porosity in a little bit more detail. So here's hydrogen. Again, this is really associated with aluminum die castings. And what we're showing here in this diagram on the right is the amount of hydrogen that can dissolve, that's the y-axis, in aluminum as a function of different temperatures. And so on the left axis, we've got this kind of strange unit, cc's of hydrogen per 100 grams of aluminum, which is often how it's quoted. But on the right, we're seeing basically weight percent hydrogen. And then we're looking at temperature, and this vertical line here is at 1220. That's the melting temperature of pure aluminum, which is what we're looking at here. And so you can see as you go to high temperatures, we can dissolve a lot of hydrogen into the liquid aluminum. However, at low temperatures, we can only dissolve a small amount. Note that this is a log scale, so that's significantly lower, hundreds or thousands of times lower in terms of solubility. So what happens if you do dissolve hydrogen? Then during solidification, as we're cooling, then the solubility, the hydrogen is no longer soluble in the solid phase, and it comes out of solution, and it just precipitates all over, and you get those pinholes that I showed earlier. And so this effect tends to be relatively small. For regular die castings, we don't really concern ourselves with it because there's more important sources of porosity. But if we're producing high integrity castings where we're trying to get all the porosity out of the castings, then it can become important. Let's talk about entrained air. We talked a little bit about this in the last webinar. On the picture on the top right, there's this kind of a large gas pore here. Shows an example. Air can become trapped at many locations during die casting, in the sleeve, in the runner, during the filling of the cavity itself. And so we can adjust process parameters to try and minimize air entrapment. Venting, as we talked about last week, is also very important. We need to make sure that it's adequate, both in terms of its size as well as in the correct location. In the extreme case, as we talked about, we can use vacuum to remove most of the air from the cavity before injecting the liquid metal. So the third source is liquids, water, lubricant, hydraulic oil, heating oil, and if we have these pre-existing in the cavity when we inject the liquid metal, then they will tend to, if they're not totally evaporated, then they will tend to vaporize as the hot metal comes through, and this is going to produce gas porosity in our castings. And these can come from things that we purposely add, such as the lubes and the water, or it can come from things leaking into the cavity. If we have a hydraulic oil leak or a heating oil leak or a cooling water leak, those two are going to vaporize and cause gas porosity. And sometimes we can tell the source of the gas porosity from the color of the internal surface of the pore. It's kind of difficult to see from this picture, but in this picture they look kind of dark, in which case it's burnt lubricant. If they're shiny, then it's either air or water. So it's worth also talking a little minute to kind of talk about the fact that many problems, as we talked about right at the beginning, can relate back to porosity. So, for example, if we look at die castings that leak, if we have a die casting that's used in a pressure-tight application, this can occur due to shrinkage. Maybe the last part to solidify, we're going to get shrinkage. We're not doing a good job of feeding it, and that can provide the leak path, and maybe that's why the die casting is leaking. So leaking is a different type of defect, but again, the origin goes back to porosity. If we have a bad die filling behavior, that can also provide a leak path. So flow, for example, if we have filling the die from two different directions, and maybe what we'll do is we'll get flow lines. You can kind of see here on the left-hand picture, we've got two flow lines, a bit more obvious in the right-hand picture. And so when the flows meet, potentially we can trap some air. If they don't fully re-weld, then we can get a leak path along the flow paths, again, basically caused by air entrapment. So if I understand the fundamentals of how to fill a casting, how to solidify a casting, I can control defects such as leaking. So how do I reduce leaking? Different ways. Firstly, you can impregnate, in which case we just fill the pores, fill the holes with a plastic type material. It's not getting rid of the cause of leaking, we're just filling the holes. But that's quite common in die casting. We can reduce the porosity. That obviously is going to reduce leaking. We can avoid removing the skin. We'll talk about this a little bit later, but with die casting we tend to get a dense porosity-free skin on the casting while the pores are located towards the center of the casting. So if we don't remove that skin, don't machine it away, then that's really good for leak-type applications and we can avoid leaking. Obviously knit lines we just talked about in terms of controlling how the liquid metal fills the die. Hot tearing is also related to shrinkage porosity, where we're producing actual cracks in the die casting. So the example is shown here on the slide. This shows an example of hot tearing in a magnesium casting alloy. This was tests actually produced in at a university, but will certainly occur in real castings. And what they were doing here, if we look at the castings themselves, obviously on the left we've got a simulation, on the right we've got pictures of real castings. And what the researcher did is he actually applied a stress to this, and you can see he was able to kind of get some information on how big a stress will cause cracking. So certainly this can be considered an extreme case of shrinkage porosity. Shrinkage porosity causes contraction, develops stresses. We're casting in a metal mold, so the casting is going to give well before the mold gives, and therefore we can pull the casting apart if we design it really, really badly. So again, if I understand shrinkage and porosity, I can also understand how hot tears and hot cracks form in a die casting. Okay, so we've kind of talked about the defects. So obviously begs the question is, how do I control these defects? And first we're going to talk about process control. And I guess that also begs the question is, can I indeed use process control to control the level of defects in my castings? And the answer is yes and no. Yes, I can have some effect with the process, but certainly it's possible to design a casting where I, as a process engineer, just cannot eliminate the porosity in the casting. So this is why the design is very important. If I have a good design, then I can have some real effect through control of the process. So the first question is, therefore, what knobs do I have to turn to control porosity? And here we're initially looking at shrinkage. This shows the effect of different parameters from the top, has the biggest effect, to the bottom only having a small effect. So if we look at the top first, intensification pressure, as we talked about before, I can increase this, I can push more liquid into the cavity to feed the shrinkage and dramatically reduce porosity. So intensification can have a large impact on reducing shrinkage porosity. The spray pattern. When I'm applying lube to the die, I'm going to affect the temperature of the die, and therefore I'm going to impact the solidification behavior. So by controlling the die temperature, I can control the solidification behavior and therefore impact shrinkage both in terms of the position and in terms of the amount. The third one down, we're calling it here on this chart mushy zone permeability, but basically we're going back to alloy design here. As we talked about earlier, the alloy composition can have a big impact on the freezing range. That's going to impact the solidification behavior, and that's going to impact the porosity, both in terms of the size of each individual pore and the distribution of the porosity throughout the casting. Then we get into in-gate design and some other things that tend not to have such a big impact as the first three I talked about above. Now, from a process point of view, it's not just enough to look at what's happening in the die cavity. For example, we can get air entrapment from filling-related defects because I had to fill the mold quickly in order to keep it from solidifying during filling. So how do I keep my metal hotter is a good way. So here's an example of data from a recent paper that shows how much heat is lost all the way from the furnace on the left to the die on the right, and they're using some kind of ladle to take the metal, the liquid metal, out of the holding furnace, pour it in the sleeve, and then it sits in the sleeve for a few moments before injecting. And what it shows here is that obviously we're losing heat throughout the process, but the solidification is actually starting here at this kink in the curve here. This is actually where the alloy is starting to solidify. And so what this shows is that we're solidifying the shot sleeve well before the injection starts. And so we don't have to just, from a process point of view, we don't just have to look at what's happening during injection into the die cavity. We have to look at the whole thermal management during the entire process. Now, as we talked about last week, we do have to look at how the metal fills. As we talked, generally, we go with a slow speed to control wave formation in the shot sleeve, and then we go at a fast speed to inject the metal into the cavity at a very high speed. So what it shows, remember, if we talked about last time, if we go too slow on the slow shot velocity or too fast on the slow shot velocity, then I'm going to get gas entrapment and obviously going to increase the porosity level in my castings. So here's some experimental data. What they did is that they took some castings and they x-rayed them. They also looked at the surface quality of them, and then they did density measurements to get the total porosity concentration in the castings. And what it shows is, now this is still the slow shot velocity, is that basically the slower I go, I'm reducing the amount of porosity in my castings. But what's kind of important here is even under great control, I never got the porosity concentration down below 0.3%. So I didn't get down to 0% porosity, and to go from 0.3 to 0 from a process point of view is going to be very, very difficult. Now this is kind of a busy slide, but I think we just need to concentrate on the top left. What it's talking about is the effect of the acceleration rate from the slow shot, from stationary up to the slow shot. And it's also showing the effect of shot sleeve filling on that parameter. And so here we're showing 70% shot sleeve fill. So we put enough metal in the shot sleeve for 70%, or maybe we put enough metal only for 20%. And there's lots of other die-cast parameters that affect this. But what this is showing is that when we have a low fill in the shot sleeve, it becomes much more important to control the process parameters. Let's look at 70% fill. So 70% fill are the diamonds, and you can see here for whatever acceleration rate we go at, we've always got kind of a low entrapped air volume in our castings. At 20%, however, or 30%, 30% may be easy to see, the open squares. As we go with the wrong acceleration rate, then the amount of entrapped gas, amount of porosity is high. If we go with the correct acceleration rate, then the amount of entrapped air or gas is low. And so to do this, we have to use a parabolic injection profile. And so instead of picking a single slow shot speed, we accelerate up to the slow shot velocity, up to the critical slow shot velocity. So again, this is kind of showing that we do have some wiggle room in the process for controlling and reducing the amount of air entrapments. So that was slow shot. Let's talk about the fast shot. Again here, this is another example to look at the effect of the surface quality as well as the internal quality via X-ray on the relative amount of porosity. In this case, these are the only two good castings that passed both X-ray and visual. And what's more puzzling is that the open triangles down here on the left had the overall lowest level of porosity, but they failed both X-ray and surface. So what's going on here? Maybe the lowest overall porosity is either entrapping air all in one location, or maybe move the porosity to the lowest, due to the lower speed, to an area of the casting where it's unacceptable. So when looking at any defect, I can certainly move it from a critical area to areas where I don't care about it, or maybe I care less about it. So often I have to ask the question, do I really need to get rid of all the porosity, which, as we just talked about, can be very, very difficult, or can I just move the porosity to a part of the casting where I care about it less, or I don't care about it at all? Or maybe, as we talked about, I can change the alloy and just disperse the porosity throughout the casting. Another thing we can do to reduce porosity is to delay the time when we go from the slow shot velocity to the fast shot velocity. And there's data out there that says this can help, and this is very, very important when we talk about thick wall die castings, less so for thin wall die casting. So if I kind of look at the top curve here, here's my slow shot velocity, here's my fast shot velocity, and what I've done is delay when I go from the slow shot to the fast shot. And I can maybe fill up to about 40% of the cavity this way. And what happens is as we delay the onset of the fast shot velocity, then we kind of start to fill the cavity at the slow speed. The metal fills in a less turbulent manner. And then when we fill maybe 20, 30, 40%, then we go to the fast shot and we spray the metal into the remainder of the cavity. And that tends to kind of build up a control at the beginning, and we maintain that control a little bit better as we fill the cavity. But it doesn't always work. And as I said, it depends upon cavity shape. Thin walls can be a problem. And again, as you can see in the bottom curve here, this is delaying the start of the fast shot versus the amount of relative porosity. And you can see in this case, for this casting, they were able to reduce the porosity. But again, it didn't go to zero. It went to about just less than 0.5% or so. So let's revisit the alloy composition we talked about. This comes from a paper where they were casting a thick wall connecting rod for an engine application, and they were looking at two alloys, 380. 380 is shown here. This is the aluminum silicon phase diagram, and you can see this is a melting range. And so 380 has about 8% silicon. It's got quite a wide melting range. Then they also looked at a different alloy, 383, that's shown here. Again, this is showing the melting range of the alloy, and you can see it's got higher silicon, 10.5% silicon, so it's got a shorter freezing range alloy. So initially they ran the casting with 383, the short freezing range alloy, and they couldn't make a good casting. Why? Because the castings were rejected at X-ray, because they were produced in a short freezing range alloy, as we just talked about. They would get a few large pores at the last part of the casting to solidify, and the big pores showed up on X-ray. So in some cases I might want this macro porosity because I can push it into an area of the casting I don't care about, but in this case it wasn't an option. So what do? They changed to 380. So this is a wider freezing range alloy, and as we talked about, with a wider freezing range alloy you get smaller, more distributed porosity, and in this case it was preferred because it enabled them to pass the X-ray. So in fatigue applications such as the connecting rod we were just talking about, we certainly want to minimize the size of the porosity because fatigue life in castings is generally controlled by the size of the largest pore. And so with a relatively small change in silicon concentration, we can dramatically change the porosity and dramatically improve the fatigue life of the castings. Now, the temperature of the die is also an important process parameter. So this shows a filling of a casting. We're filling it from the left-hand side here. Here's the gate of the casting. And then we're filling it from left to right. And then as it solidifies, we want to generate directional solidification. We want the right-hand side of the casting to solidify first. And then we want the solid liquid front to move back from right to left, back towards the gate. Why? Because that allows the gate to remain liquid longer. It allows the left-hand side of the casting to remain liquid longer. And as we talked about, we're going to push more liquid metal and try and feed solidification and shrinkage by pushing more liquid metal into the cavity. But in this case, we have some hot spots. We've got some hot spots here in the die by the pins. And so we're no longer going to get directional solidification. So this will end up being the last part of the casting to solidify, and therefore it's going to solidify after this section, and therefore we're no longer going to be able to feed that section, and so we're going to get shrinkage porosity in that section. So we can use internal cooling, we can use die spray to try and control the solidification behavior of the die. So that's what we're showing here. Now we're looking at a spray pattern, and so we're looking at a simulation actually here where we're going to spray the die for about 4.5 seconds, and then we're going to spray the runner for different amounts of time, anyway from 0 to 4.5 seconds, and then we're going to look at the average pore section in the casting. And so we're looking at spray time here versus percentage of pores. And so what happens when we spray the runner a lot, then the runner gets colder, that part of the casting is going to solidify faster, and therefore it's going to block the feeding of the liquid into the cavity, and we get more shrinkage porosity, and so that's what we're showing here. So as we spray the runner more, we get more shrinkage porosity in the casting. If we spray for a shorter amount of time, then the runner is going to remain hotter, it's going to solidify slower, it's going to remain liquid longer, so we can feed it longer and reduce shrinkage porosity. So how I spray the die, again from a process point of view, can dramatically affect the porosity level. So here we're looking at a slightly different thing. Now on the runner, we're always spraying for 1 second. The casting, we're spraying for 4.5. And then on the top, what happens is we're spraying for 0 suddenly. Maybe a nozzle gets blocked or something like that. So here's the base case. Here's our casting. We're feeding it from the bottom here into the casting. And we're looking at the effect of shrinkage. And the bright colors are a lot more less of shrinkage. The darker colors are less shrinkage. You can kind of see where we're getting shrinkage. And by no spraying to the top, you can see we're increasing the porosity level because, again, that part of the casting will solidify more slowly, and therefore it's no longer going to be fed by the remaining part of the casting. And we're going to increase the amount of porosity in our casting. And then here we got the insulated runner. And so let's look at the ultimate case where there's no heat loss from the runner. And in this case, obviously, this is a simulation. We can't do this in real life. But here's our base casting. Again, we're looking at porosity levels. And then here's the insulated runner. So by not removing heat from the runner, we're able to do a much better job of feeding porosity. But even in this ultimate case, we never totally get rid of the shrinkage porosity. And now we start talking about the design side of things, because now this is porosity that's introduced by the design side of the casting, because we have a heavy section here, and therefore this part of the casting is going to solidify more slowly, and therefore we're going to lose heat more slowly, and therefore we can't feed the solidification shrinkage in that area due to a design issue. So that obviously then leads us on to how do I design castings to control these defects, to minimize the level of defects in the die castings. So firstly, we need to pick the right process. This is why we spent so much time talking about in the last webinar. We've got to ask questions such as how much porosity am I allowed? Therefore, do I need a high integrity process? And if yes, which one? But if I'm just worried about leaking, then maybe I should just impregnate my casting, or maybe avoid machining areas to leave the skin intact that are leak critical areas. But these questions need to be asked early in the design process. If we're just making the casting on the right-hand side, those are just decorative. We don't really care about porosity. We're making casting on the left. We talked about last week, that shock tower, very important in porosity. So that kind of decision has got to be made early, and again, talk to the die caster. So another question you've got to keep in mind is, can I tolerate porosity? And it depends upon what the part's being used for. So here's an interesting chart showing the impact of porosity on yield strength, on the ultimate tensile strength, and on the elongation of the alloy. And we're showing it for 3 different porosity levels, A0, A2, and A4. And most die castings are going to be between A0 and A2. And what we can see here is in this area, porosity is having very little impact upon the yield strength, and that's very common. Has more of an impact on the tensile strength, and it has a big impact on elongation. So again, you've kind of got to think about what your casting is being used for, and maybe porosity isn't as a bad thing as you think it is. Then casting shape. Can you design something with uniform thin walls? Why is this important? Because we're showing here on the left-hand side, here's a casting with thin walls, as we talked about before. We tend to get this chill layer on the surface, and we only get a small layer in the middle where we get the porosity in, and a lot of the porosity gets pushed out of the casting because it solidifies so quickly and it doesn't have time to form. And so the dense skin on the left-hand side becomes a big percentage of the overall thickness of the casting. On the right-hand side, a thick wall die casting, we get the same dense skin, but the center section where we get that porosity becomes a much bigger percentage of the overall casting. And as we talked about earlier, we want to promote directional solidification, so we need to avoid thick areas that are going to solidify slowly well away from the gate, because I won't be able to feed them. So a die caster tries to gate into the thickest part of the die casting, and therefore this allows him to promote directional solidification, as we discussed before. Directional, you want the extremities of the casting to solidify first, and then back towards the gate. We also want to take the advantage of design flexibilities that we get with die casting. So, for example, if we're looking at these 2 castings shown on the bottom left, one of them is a horrible design for die casting, one of them has been optimized for die casting. The one on the left is a bad design. This was basically designed for machining, probably out of some kind of bar or other. It's got thick walls, it's got thin walls, it's got sharp corners. Very bad design for die casting. On the right-hand side, that part's been redesigned for die casting. Now we have uniform wall thickness, we've got radii on the corners, and this is a good design for die casting, and so we're going to get a higher quality die casting. So again, during design, try to visualize the flow, visualize how it's going to solidify, or more importantly, go talk to the die caster and have some input into the design. Now, there's plenty of information out there. NADCA puts out a product design for die casting book, and this provides great examples of things you should do and things you shouldn't do. So here's a quick look at for fillets. And so here's a really bad design. It's not recommended because you've got sharp corners on it. Well, we've rounded the corner, but now we've designed a heavy section into it, and therefore that's less desirable. Optimal design here is where we've got both sides of the corner, uniform wall thickness as we go around the fillet. And so another example of effective part design on porosity is heat traps. When we put corners into die castings, we can get heat spots. We're going to get much more heat flow on the inside here than on the outside, and so the die is going to get hotter on the inside than the outside. And so here again, fillet, we're going to get a heavy section here, heavy section here. So you got to think, do you really need that fillet, or not. If you can get away without it, don't put it in. You're going to produce a problem in the casting. Here again, talking about die design. Down here, we have rounded the corners to try and minimize the hot spot we talked about before. Or maybe we can put in a different material. This is an amberloy, which is a tungsten alloy that has better heat flow characteristics, and therefore will tend to keep this part of the die cooler. So again, having a discussion with a die caster up front is important, because this has to be thought through early in the design process. Then cooling lines, obviously the die caster needs to put cooling lines into his die, into critical areas. There's a lot of literature out there about how to control this. So again, talk to the die caster because he's going to want to put cooling lines in certain places. And again, having this discussion early, make sure we get the optimum design. Vents also, depending upon what process you're going to use, is going to depend upon where the vent is located. You want the vent at the last part of the casting to fill. Obviously, that's where the air needs to be extracted from. On the left, we have semi-solid, where the last part's to fill on the right-hand corners. With conventional die casting, the last part to fill is on the left-hand corners. So again, we need to kind of think this through. You have to be able to provide locations so the die caster can put vents into these different locations. So the last part I want to talk about is design for die building, gating, thin walls. We need to make sure that you avoid design features that can produce defects. So examples is slide cores. When I need to inject the liquid metal in a cavity, maybe I want to gate it where you've put a slide or where we're going to need to put a slide. And so this then forces the die caster to put the gate in an area that's not ideal, maybe put vents in areas not ideal. So again, having this discussion early on with the die caster allows a discussion to go backwards and forwards in terms of how to design this part, and therefore for the optimum filling and optimum castability. Okay, so this leads us to the point of measuring defects. It's all well and good about talking about controlling defects, but obviously we can't control what we can't measure. So how do we do this in die casting? Well, there's various ways. The simplest approach is to look at the castings and therefore kind of work out where you think the porosity is, and then just cut it up. Saw cut it, maybe grind polish the surface, and that allows us to directly examine the cut surface. And again, if we've got jagged pores, that's probably latent solidification, it's probably shrinkage. If we have smooth pores, that's probably gas, and that allows us to address the source and the origin of the porosity. Maybe we're doing some destructive testing. Maybe there's a functional test on the part that has to be done. So once the part's broken, we can look at the fracture surface, and the areas shown here in red, these are gas pores, clearly gas pores from how uniform they are, and again, that allows us to easily tell the source of the porosity. X-ray, if we don't want to cut the casting, obviously X-ray is the most common non-destructive process. There is a ASTM standard 505, and that kind of gives us information, so we can pick an area of the casting shown in red, compare it to ASTM 505, and we can say the porosity shouldn't be more than level 1, level 2, level 5, or whatever. So the problem with this is that we have to kind of look at the distribution of porosity and how that's going to affect porosity. What we're showing here in a cartoon, all these pores are the same volume. They're all 5 cubic inches of air, but obviously the distribution is going to have a huge impact upon the porosity and performance of the casting. And so we really need to understand this as we're going forward in terms of measuring and designing our castings. SEM, scanning electron microscope, is another way of looking at the defects. It's a bit more exotic. Only do it if you've really got a problem. But a couple of advantages: it gives you much better depth of field. You can look into the holes a lot better. And we can also get chemical information. So in this case, it looks like the defect was a piece of iron that got into the casting. Then there's a whole range of other different methods: ultrasonic, eddy current, electrical conductivity, performance testing, functional testing, and all different ways of looking at our castings. So what does this mean? Obviously, we can't measure what we can't see, but often we can rarely measure what we want directly. A lot of the measurements can be indirect. But we really have to have a good knowledge, therefore, of what is measured, how it's measured, and what the results actually mean. One other thing is that within die casting now, we're starting to use this a lot more, where we can control the process to control the level of defect. So if we can come up with a correlation between parameters, maybe such as die temperature or porosity, or intensification and porosity, therefore we can define optimum ranges for die temperature and intensification pressure, where we know we're producing good castings, and if we're outside that range, we're producing bad castings. And so that becomes very useful within the die casting process. Another possibility, we can do offline tests. This is a reduced gas test. This tells us how much hydrogen is dissolved in the aluminum. Again, really good for controlling the process. Alloy controls. Maybe I need to control the composition of the alloy tighter than the nominal alloy specification, and this is very common, certainly with automotive. And then also environmental humidity. Here's an example of a casting. One on the right was produced in Asia, where the humidity was very high, and they couldn't get the vacuum level down to the right level. So they moved it to a different part of the world where the humidity was lower, and that allowed them to get the correct vacuum level within the casting. Okay, so that's it for today. So in terms of the conclusions, so defects within castings, primarily porosity related in die casting, they come from the characteristics of the die casting process. And together, the casting producers and the die designers and the part designers should be able to manage these characteristics to reduce the chance of defects. And then obviously the idea is to have the discussion early between the various people, the part designer, the casting producer, and probably the die designer too, to talk about how you're going to gate it, how you're going to cool it, how you're going to inject it, where you're going to put various features. And if you can do that and optimize the part design early, it's going to run much better in the die casting process. So that's all we have today. Again, these are the sponsors that are going to provide you with a copy of today's webinar. And again, we've got a little bit of time for questions, if any of you have questions about what we've been talking about today.
Hi, everybody. So as Steve said, we're going to open it up for questions. There's a couple ways that you can ask questions. Within your control panel, there is a text box. If you click within the text box, type your question in and hit submit, we'll get it on our end. The next thing that you can do is if you're calling it on a telephone or if you have a mic set up, you can click that little hand icon. We will call on you and unmute you, and you can ask your question out loud. And last but not least, feel free to email us at webinars@diecasting.org, and we will put you in contact with Steve with any questions that you might have. So with that, we're just going to hang out on the line for a few minutes and see if anything comes through.
All right. Thick and thin casting several times. What thickness characterizes the cutoff before between thick and thin? Well, that's I mean, generally a thin wall die casting is somewhere 2-3 millimeters. So what's that? 80 to 120 thousandths of an inch. So if you can kind of stay within that kind of range, obviously it depends upon the size of the casting. The bigger it gets, obviously the thicker the wall we need in terms of filling it. So that's not just that's not a hard and fast rule. But when we start to get around a quarter of an inch or so, or bigger than that, that's generally getting into the arena of a thick wall die casting or a thicker wall die casting. So there's some kind of general, I would say rules of thumb, but some kind of direction in terms of thin wall and thicker wall castings. Okay, that's the only question I see so far.
That is also the only question that I see. If you're in the process of typing a question in, that's totally fine. I know sometimes it takes a couple of minutes to type that in. If you want to click that little hand icon, that'll just let us know that you're typing something and that we should remain on the line. Okay, I don't see any hands raised. So with that, again, jot down the email address webinars@diecasting.org and feel free to email us with any questions that you might have, and we will pass those on to Steve for you. So with that, Steve, thank you for presenting today, and everybody else, thank you for attending, and we look forward to seeing you all on another webinar. Thanks, guys. Have a good day. Bye.
Thanks, everybody.